Hi everyone. I'm sorry for being late. Welcome to our very first Analyst Day for Autonomy. I really hope that this is something we can do a little bit more regularly now to keep you posted about the development we're doing with regards to autonomous driving. So we wanted to find the best possible chip for full autonomy. And we found out that there's no chip that's been designed from ground up for neural nets. So we invited my colleague Pete Bannon, the VP of Silicon Engineering, to design such chip for us. He's got about 35 years of experience of building chips and designing chips.
He's just the best chip and system architect that I know in the world, and it's an honor to have you and your team at Tesla.
I was hired in February of 2016. I asked Elon if he was willing to spend all the money it takes to do full custom system design. And he said, well, are we going to win? And I said, well, yeah, of course. So he said, I'm in. And so that got us started. We hired a bunch of people and started thinking about what a custom design chip for full autonomy would look like. We spent 18 months doing the design, and in August of 2017, we released the design for manufacturing. We got it back in December, it powered up, and it actually worked very, very well on the first try. We made a few changes and released a B0 Rev in April of 2018. In July of 2018, the chip was qualified, and we started full production of production quality parts. In December of 2018, we had the autonomous driving stack running on the new hardware, and we were able to start retrofitting employee cars and testing the hardware and software out in the real world. Just last March, we started shipping the new computer in the Model S and X, and just earlier in April, we started production in Model 3. So this whole program, from the hiring of the first few employees to having it in full production in all three of our cars, is just a little over 3 years, and is probably the fastest system development program I've ever been associated with. Here's what it looks like. Over there on the right, you see all the connectors for the video that comes in from the 8 cameras that are in the car. You can see the 2 self-driving computers in the middle of the board, and then on the left is the power supply and some control connections.
Any part of this could fail, and the car will keep driving. So you could have cameras fail, you could have power circuits fail, you could have one of the Tesla full self-driving computer chips fail, car keeps driving. The probability of this computer failing is substantially lower than somebody losing consciousness. That's the key metric, at least an order of magnitude.
Collect lots of information from the world around you. Not only do we have cameras, we also have radar, GPS, maps, the IMUs, ultrasonic sensors around the car. We have wheel ticks, steering angle. We know what the acceleration and deceleration of the car is supposed to be. All of that gets integrated together. It's packaged in a 37.5 millimeter BGA with 1600 balls. Most of those are used for power and ground, but plenty for signal as well. If you take the lid off, it looks like this. You can see the package substrate, and you can see the die sitting in the center there. If you take the die off and flip it over, it looks like this. There's 13,000 C4 bumps scattered across the top of the die. And then underneath that are 12 metal layers, and which is obscuring all the details of the design. So if you strip that off, it looks like this. If we use all 12 CPUs to process that network, we could do 1.5 frames per second, which is super slow, not nearly adequate to drive the car. If we use the 600 gigaflop GPU, the same network, we'd get 17 frames per second, which is still not good enough to drive the car with 8 cameras. The neural network accelerators on the chip can deliver 2100 frames per second.
Well, how could it be that Tesla, who has never designed a chip before, would design the best chip in the world? But that is objectively what has occurred. Not best by a small margin, best by a huge margin. It's in the cars right now. All Teslas being produced right now have this computer. We switched over from the NVIDIA solution for S and X about a month ago, and we switched over Model 3 about 10 days ago. All cars being produced have all the hardware necessary, compute and otherwise, for full self-driving. I'll say that again. All Tesla cars being produced right now have everything necessary for full self-driving. All you need to do is improve the software. We care about one thing, self-driving. So that it was designed to do that incredibly well. The software is also designed to run on that hardware incredibly well. And the combination of the software and the hardware, I think, is unbeatable. And I think if somebody started today and they were really good, they might have something like what we have right now in 3 years. But in 2 years, we'll have something 3 times better. Man, I'd like to meet the person that could do that, because I would hire them in a heartbeat. Yeah, so that'd be a hard problem. Yeah, do you want to? I mean, we do encrypt it's a hard chip to crack. So if they can crack it, it's very good. If they can then crack it and then also figure out the software and the neural net system and everything else, they can design it from scratch. Nobody has the fleet.
We have our Senior Director of AI, Andrei Karpathy, who's going to explain all of that to you. Andrei has a PhD from Stanford University.
There's a lot of PhDs from Stanford. That's not important.
Yes.
Okay, we don't care. Andrei started the computer vision class at Stanford. That's much more significant. Andrei is like really one of the best computer vision people in the world, arguably the best.
So Pete told you all about the chip that we've designed that runs neural networks in the car. My team is responsible for training of these neural networks. What we are seeing here is a stream of videos from across the vehicle, across the car. These are 8 cameras that send us videos, and then these neural networks are looking at those videos and are processing them and making predictions about what they're seeing. They know nothing, and it's really hard to wrap your head around this. So as an example, here's a cute dog, and you probably may not know the breed of this dog, but the correct answer is that this is a Japanese Spaniel. Now all of us are looking at this, and we're seeing Japanese Spaniel, and we're like, okay, I got it. I understand kind of what this Japanese Spaniel looks like. And if I show you a few more images of other dogs, you can probably pick out other Japanese Spaniels here. So in particular, those 3 look like a Japanese Spaniel and the other ones do not. So you can do this very quickly, and you need one example, but computers do not work like this. They actually need a ton of data of Japanese Spaniels. So this is a grid of Japanese Spaniels, showing them, you need thousands of examples, showing them in different poses, different brightness conditions, different backgrounds, different crops. You really need to teach the computer from all the different angles what this Japanese Spaniel looks like. To get neural networks to work well, you require these 3 essentials. You require a large data set, a varied data set, and a real data set. We start with a seed data set that was potentially sourced at random. We annotate that data set, and then we train neural networks on that data set and put that in the car. And then we have mechanisms by which we notice inaccuracies in the car when this detector may be misbehaving. So for example, if we detect that the neural network might be uncertain, if we don't perform very well on lane line detection on tunnels, then we can notice that there's a problem in tunnels. That image would enter our unit tests so we can verify that we're actually fixing the problem over time. But now what you do is to fix this inaccuracy, you need to source many more examples that look like that. So we ask the fleet to please send us many more tunnels, and then we label all those tunnels correctly. We incorporate that into the training set, and we retrain the network, redeploy, and iterate the cycle over and over again. So here's a video showing the autopilot detecting that this car is intruding into our lane. We ask the fleet to please send us data whenever they see a car transition from a right lane to the center lane, or from left to center. And then what we do is we rewind time backwards, and we automatically can annotate that, hey, that car will in 1.3 seconds.
I mean, the crazy thing is, the network is predicting paths it can't even see with incredibly high accuracy. It can't see around the corner, but it's saying the probability of that curve is extremely high. So that's the path. And it nails it.
So here's an example of predictions of that. So in circles, I'm showing radar objects, and the cuboids that are coming out here are purely from vision. How much data do we get from the fleet? So it's really important to point out, it's not just the scale of the data set, it really is the variety of that data set that matters.
What happens to the rest of the industry that's building their autonomy solutions on LiDAR?
They're all going to dump LiDAR, that's my prediction. Mark my words.
Free data centers for you to do computational? Is that a huge future opportunity for Tesla?
It's current.
A current opportunity, and that's not really factored in for anything yet. That's incredible. Thank you.
We're at 70 million miles already for Navigate on Autopilot. It's something we're like really, really cool. We have 8 cameras, but then we also have additionally 12 ultrasonic sensors, or radar, an inertial measurement unit, GPS, and then one thing we forget about is we also have the pedal and steering actions. So not only can we look at what's happening around the vehicle, we can look at how humans chose to interact with that environment. That neural network is not making one prediction about the world. It's making many separate predictions, some of which actually audit each other. So as a real example, we have the ability to detect a pedestrian. Lastly, we can combine that with things like the radar and the ultrasonics to build these extremely precise understandings of what's happening in front of the car. We can use that both to learn future behaviors that are very accurate. We can also build very accurate predictions of how things will continue to happen in front of us. And we can see what they would have done in a real world scenario, such as this car that's overtaking us very quickly. And this is taken from our actual simulation environment, showing different paths that we have considered taking and how those overlay on the real world behavior of a user. When somebody takes over, we can actually get that clip, try to understand what happens, and one thing we can really do is we can actually play this back, again in an open loop way, and ask, as we build our software, are we getting closer or further from how humans behave in the real world? 9 million successfully accepted lane changes. Relax, put your hand on the wheel, and just oversee what the car is doing. And in this case, we're actually seeing over 100,000 automated lane changes every single day on the highway system.
Acknowledge all those lane changes have occurred with 0 accidents.
That is correct.
Hundreds of thousands going to millions of lane changes and 0 accidents is, I think, a great achievement by the Tesla team. So we've gone through the future of self-driving, where it's hardware, it's vision, and then there's a lot of software. In 2019, no car that can compete with the Model S of 2012. It's 7 years later. Still waiting. So all these things, I said we would do them, we did it. Said we'd do it, we did it. We're gonna do the RoboTaxi thing too. I get it done. And the Tesla team gets it done. So what we're gonna do this year is we're gonna reach combined production of 10,000 a week between S6 and 3. Feel very confident about that. And we feel very confident about being feature complete with self-driving. Someone will be able to add or remove their car to the Tesla network. So we expect this to operate, it's sort of like a combination of maybe the Uber and Airbnb model. So if you own the car, you can add or subtract it to the Tesla network, and Tesla would take 25 or 30% of the revenue. So when you use the car, we'll show you our ride-sharing app. So you'll be able to summon the car from the parking lot, get in, and go for a drive. We'll do Model 3, S3 and X as taxis, but we made an important change to our leases. So if you lease a Model 3, you don't have the option of buying it at the end of the lease. And as I said, where in any locations where there's not enough supply for sharing, Tesla will just make its own cars and add them to the network in that place. So the current cost of Model 3 RoboTaxi is less than $38,000. We expect that number to improve. The cost of ride sharing is, according to Uber and Lyft, is $2 to $3 a mile. The cost to run a RoboTaxi, we think, less than 18 cents a mile. You say, what would be the probable gross profit from a single RoboTaxi? We think probably something on the order of $30,000 per year. That no one needs to pay attention. Meaning you could go to sleep from our standpoint, if you fast forward a year, maybe a year and 3 months, but next year for sure, we will have over 1 million RoboTaxis on the road. So yeah, the cars would just automatically park and automatically plug in. There would be no human supervision required. The auto industry is very slow to adapt. I mean, like I said, there's still not a car on the road that you can buy today that is as good as the Model S was in 2012. And they really need to be electric because the cost of operation of a gasoline diesel car is much higher than an electric car. So any RoboTaxi that isn't electric will absolutely not be competitive. Once regulators are comfortable with us not having a steering wheel, we'll just delete that. And for cars that are in the fleet, obviously with the permission of the owner, if it's owned by somebody else, we would just take the steering wheel off and put a cap where the steering wheel currently attaches. Today is that it's financially insane to buy anything other than a Tesla. If you buy a car that does not have the hardware necessary for full self-driving, it is like buying a horse. And the only car that has the hardware necessary for full self-driving is a Tesla. You can't look in all directions at once. The car can literally look in all directions at once with multiple cameras. Humans are able to drive just by sort of looking this way, looking that way. They're actually stuck in their driver's seat. They can't really get out of the driver's seat. So it's like kind of one camera on a gimbal, and is able to drive. A conscientious driver can drive with very high safety. The cameras in the cars have a better vantage point than the person. Thanks everyone. Please enjoy the drives. Thank you.
Thank you very much.